All right, so we're going to start the second part of Unit 10, which is the sound part, Chapter 20. So we're talking about sound, the speed of sound, how reflection happens with sound and refraction, which can be applied to any wave situation. We'll get into energy in sound waves, kind of forced vibrations, natural frequencies of vibrations, and the idea of resonance a little more, interference, and beats in their applications. So again, sound is a form of energy that exists whether it's heard or not. All right, we're just used to sound in the range that we can hear, the audible range for humans, but there are sounds that we can't hear. And most sounds are waves produced by the vibrations of matter. And that vibration stimulates something more massive, and then eventually, gets into the air, and we hear it once it vibrates the air. And it's a longitudinal wave. So the sounds that we can hear generally range from 20 to 20,000 hertz, especially if you're younger. Some people can hear a little higher, some people can slightly hear a little lower, but that's generally what you can hear. And as you get older, it gets weaker. Frequency, though, is also referred to pitch when we're talking about sound. So you hear the term pitch perfect. That means somebody who has an idea of exactly what frequencies they're hearing. That's what somebody is when they've got good pitch. So again, your hearing, other than getting older, you can also damage it. So sticking the earbuds in your ear all the time with it cranked up to 11, that's going to damage your hearing over time. So sound waves that are below that 20 hertz range, we call that infrasonic. It's too low for us to hear. Some animals can hear it, but humans can't. Then you have sound waves that are above 20,000 hertz. Those are ultrasonic. Again, some animals can hear it. So dolphins and bats, they use that for echolocation. Although again, infrasonic, ultrasonic means we can't hear it. It's either below hearing or above hearing. That's what it means. So what actually happens with a sound wave is we're vibrating air, and you're getting compressions of that air and rarefications of that air. Okay, so areas of higher pressure and lower pressure. Compression, high pressure; rarefication, lower pressure. In that longitudinal wave. So that means that the wave is moving in the same direction as the energy. Okay, and it could be traveling through a solid, liquid, or a gas. We're just used to hearing it through gas, right? Through air, occasionally through helium. That's where you sound like a chipmunk. And our wavelength is going to be the distance between the successive compressions or rarefications. So I could say that my wavelength was from like here to here. There's my lambda. Or I could say it's from like here to here. That could also be my lambda. So now, one way we're used to kind of generating sound from electronically produced sound is through a speaker. And all a speaker is some paper cone that can vibrate the air. Microphones are kind of the reverse, and it applies the electromagnetism that we talked about with Faraday's law and Lenz's law to move magnetic particles near coils, either one way or the other, to either produce the sound or to pick up the sound. And that's how a speaker or a microphone work. So air molecules next to that speaker will vibrate, producing those compressions or rarefications of the air, and that's what we end up hearing from the speaker. Gets into your ear, and you vibrate your eardrums, gets into all those little pieces within the ear that you can learn about in anatomy physiology, that actually allows your brain to pick up on that signal as an electrical impulse. So our speed of sound depends on the medium it's moving through. So we're used to hearing it in air. Speed of sound in air is somewhere between 331 for really cold air, 343 for warm air, or room temperature air. Occasionally, like I said, people are crazy. They inhale some helium. You sound like a chipmunk. That's because you're getting the speed of sound through that to be 965 meters per second, so almost 3 times faster than you're used to hearing it through. Water is not that compressible, so sound travels even faster. That's why if you've ever heard somebody try to talk underwater, it sounds really distorted. And then even solids. If you ever watched any old movies, they'd always put their head to the ground to try to listen for oncoming stampedes or oncoming trains in the old westerns. And that's because the speed of sound is 17 times greater through the solid than it is through the air. So you're going to hear it through the ground before you'd ever hear it through the air. So, a little example here. You watch a person chopping wood on a winter day, and you note that after the last chop, you don't hear it till 1 second later. How far away is the chopper? Answer would be 331 meters per second, because on a cold day, air is at about 331 meters per second for a velocity. If it's 1 second later, you multiply it out and you say it's about 331 meters. So now you hear thunder 2 seconds after you hear the lightning flash, okay? Because the lightning is almost instantaneous. It's traveling at 3 times 10 to the 8th meters per second. during the summer rainstorm. How far away is that lightning? Well, generally in the summer, it's warmer, so we go with 343 for the speed of sound in air. But if it's 2 seconds, it'd be 343 times 2, which would give you 686. So reflections. So the process in which basically sound encounters some surface and then bounces back. Basically, any wave can reflect, whether it's a water wave or a sound wave or a mechanical wave of some sort. So with sound specifically, it's sometimes called an echo. And if you get multiple reflections within a room or an instrument, they call that reverberation. If you've ever been to certain areas where you have parks where there's a cliff or something, you can get echo across a lake. Like I think of in New Hampshire, there's a place actually called Echo Lake near Cathedral Ledge, and you yell out across the lake, it bounces off a cathedral ledge, and you hear it back, delayed by a second or so. That's an example of an echo where the sound reflects off of the sheer cliff back at you. Reverberations, you can be in some rooms that are, again, designed for hearing music or movie theaters, and the sound will seem to reverberate in that room. Now, sometimes you don't want reverberations in the room because you want to hear just the pure sound that's happening. So there's the field of acoustics. So you actually study how sound will behave. So in concert halls, you try to balance the reverberation and the absorption. So they actually design things that will reflect or redirect sound. Think almost like a mirror for sound, or something that would absorb it. So just like a dampener. They do this in recording studios especially. They'll put paddings on the walls that collect the sound because you're in a very small space and you don't want that sound reverberating while you're recording. And people study this field to figure out what's the best way for a space to get the optimum sound off the stage from the performers out to the audience without it reverberating too much in the room. So then you get refraction. So refraction is the bending of a wave. So this could be, air being warm or cool will bend a sound wave one way or the other. This is why on a cool night, again, if you're near like a lake, I think again up in New Hampshire in the lakes region like Winnipesaukee, you can hear sound way across Winnipesaukee at night because it's cool air over the water, slightly warm air above, and it refracts the sound downward and it kind of travels right across the lake. But on a hot day, when you get like hot tar and you try to yell, that sound gets kind of bent upward because it's much warmer over the tar and the sound bends away and you don't hear it as well. It doesn't travel as far. With light, refraction, you're more used to seeing things like prisms. So prisms bend the different colors of light because they're at different speeds slightly as they come out of the prism. So other applications of sound. So we talked about things like ultrasounds. Those ultrasonic sounds can be used for echolocation by animals, or within the human body we can use it for imaging. Imaging tumors, imaging babies, because basically it bounces off, reflects off of some sort of tissue or whatever, and we pick up that sound with almost like a microphone, and we can get an image from that to figure out that delay in the echo. Another thing called resonance. So sometimes just with any wave, things can resonate. So a vibration that sets up that is somewhat forced, might feel like if you're in a building with like heavy machinery running, you might start feeling vibrations through the floor, or if large trucks are going over like a bridge, you'll feel those vibrations in the bridge. But you can also have natural frequencies. So like imagine when you're on a swing, if somebody's pushing you at just the right frequency, they're pushing you at just the right time, you start to go higher and higher and higher. And that's because of, again, that forced vibration. Well, these natural frequencies, these forced vibrations, can be bad if it happens in the real world. And a prime example of this is the Tacoma Narrows Bridge. So this was a bridge that, just because of the way it was designed, its natural frequency was just about that of the 40-mile-per-hour wind that seemed to come down through the Tacoma Narrows, through this river valley. And over time, with this wind, again, light wind, 35 to 40 miles per hour, just tapping on the bridge, it eventually tore the bridge apart. So we're not talking like hurricane force winds. We're talking like light winds that we get here on a regular day, just tore the bridge apart over time because it caused it to start resonating. Other examples of resonance would be if you take and run your finger around the top of a crystal glass. That slight vibration you make from your finger tapping the glass, the fingertip, makes it start to resonate and actually makes a sound. So we've already talked a little bit about interference, but just to recap, Same thing can happen for sound. You could have, constructive or destructive interference happen. So basically the waves add together, make a bigger wave, cancel out, make a weaker wave, or cancel out altogether, depending on constructive, destructive interference. So for sound, here's what's really happening. And it gets into the idea of the air molecules lining up, and you're getting those higher pressure and lower pressure areas. So for looking here, I get very high pressure when they're in sync. Okay, so it's actually high pressure areas that I'm detecting. But if they cancel out, it causes the pressure overall down here to kind of equalize. So you don't hear the sound. And that's what's happening. There's nothing to detect there. There's no waveform to detect there. And that's specifically how sound kind of deals with constructive, destructive interference. And again, people have made lots of money on understanding this. Dolby surround sound, okay? Being able to make you think that something's moving in the room from left to right. So, for the longest time, we only had mono sound. Then you get stereo sound. So then you can get things moving left to right. Then you get, Dolby 5.1. Now things can move left to right, front to back, up and down. And then you can start to get things that sound like they're below you and above you when you get to the 7.1 systems, which is really fun. With those constructive and destructive interferences, sometimes they don't completely act destructive or completely act constructive, and you get this thing called beating. So this is when you get periodic areas where it's louder, and then periodic periods where it's softer. Okay, so you get an area here, right, where it's constructive, right? An area here where it might be a little destructive. Another area where it might be constructive. And just that adding together overall makes it into a new waveform. Standing waves. Okay, we've already talked about standing waves in string, but what about in air, columns of air? Well, the most simple form of it is if I kind of blew across top of the soda bottle, all right, a closed tube situation. Well, what will happen is at the end where it's closed off, I have a node form. The end where it's open, though, because I'm moving the air rapidly, I get an antinode. Okay, so I end up with my first harmonic, or my fundamental, being that length there is about a quarter of the wavelength. So lambda is equal to 4 times the length. All right? And again, if I go through this whole process of using V equals lambda F, I end up that the fundamental frequency will be equal to the wave speed, which for air will be the speed of air, 343 normally for room temperature air, divided by 4 times the length of the tube. Now, the interesting thing that happens here for us, though, is you can't have every single harmonic, all right? So if I went up to the second harmonic, what would happen for me is, and I can draw it out here, I'd have to have a node and a node, which can't happen. Because I'm moving here, I have to have an antinode. I can't have a node. No, that's bad. So that means I skip and I go to the situation I've got drawn here, node, antinode, node, antinode, which is really the third harmonic, right? I skip over the second and I go right to the third because I would never hear the second harmonic, all right? It's not to say the second harmonic couldn't set up in the tube. It's just I could never hear it. It wouldn't actually let air out of the tube. So we end up with 3 times F1. And then if I went to try 4 times F1, again, that can't happen. So I go to the next one, be 5 times F1. All right? So I start realizing that for standing waves in a column of air in a closed tube, that it follows that whole kind of F1 equals V over 2L, but it's going to have that N times F1 situation where N is 1, 3, 5, just the odd integers. I can't have the even integers, okay, for the closed tube. All right. For the project, though, you only really have to worry about, calculating based on F1 because we're just assuming you're building around the fundamental frequency. If you hear the other ones, that's just the way your instrument is designed, is allowing itself to resonate at those other frequencies. As for the open tube would have to have an antinode at either end. So then our first harmonic or fundamental gives us basically that lambda is equal to 2 times L. And then it allows us to set up that second harmonic and that third harmonic, which is a little different. Okay, so standing waves in the pipe allows all the different harmonics. So there we end up with that F1 is V over 2L, and we can have every integer. So F1 is, N times F1 for the different integers, but it's still N V over 2L. Okay, so we're just, again, going to calculate just F1 for the instruments, but we're going based on that. N equals 1, 2, 3, 4, so any integer for the harmonics that it could produce. So now the other fun thing, the Doppler effect. So what if our source or our observer are moving? Okay, so think of like an emergency vehicle, fire truck, police cruiser, that's coming either towards you or away from you at high speed. You notice the siren's pitch, the siren's frequency there changes. It either gets higher pitch as it's coming towards you, lower pitch as it's going away from you. Or even if you're the one moving towards the siren, you might hear that distortion happen also. So imagine a parked police cruiser and you're driving towards it versus after you drive past it. And that's all described by the Doppler effect. Doppler effect also has other applications to other waveforms. So we use Doppler in terms of radar to figure out how weather systems are moving. We use it in astronomy to figure out how stars are moving, right? So within the relative motion of the galaxy, if something's moving away from us, we might detect that that light is one color versus if it's moving towards us. So anything moving towards us gets blue shifted. Anything moving away from us gets red shifted. So there's a certain color the star should be based on what chemistry tells us because of the makeup of the star. But if those spectral lines that hopefully you learned about in chemistry move more towards the red and more towards the blue, we know that star's either moving towards us or away from us. Okay? Again, based on the Doppler effect. How to explain it simply is the wave fronts, or the distance between the wave crests, either compress or expand. All right? So what happens here, lambda goes down, which means the frequency goes up. On the other side, lambda goes up, which means the frequency goes down. So we start to see why on the front of the vehicle, as it's moving towards us, like if it's beeping its horn, running a siren, we hear a higher pitch frequency. As it's going away, we hear a lower pitch frequency. Kind of a generalized equation that we can find is that the frequency that the observer hears is equal to the frequency the source is producing, the siren, whatever it is, times this kind of really big complex looking fraction. So really I could put some parentheses around this, and you probably should too on your paper, and it's 1 over versus the 1 over this. So 1 is if the observer is moving, 1 is if the source is moving. So on the top deals if you're the one moving. The bottom deals if the source is moving. But theoretically, you both could be moving at the same time. So if the observer is moving, it's 1 plus minus the velocity of the observer over the velocity of the sound. If it's the source moving, it's 1 minus plus the source over the sound. Okay. Now, if you notice here, right, they're different. It's plus, minus, minus, plus. So whatever's on the top has to deal with the observer or the source moving towards. Okay, so coming towards the observer. With the sound, is just velocity sound, whatever. But on the bottom, this is kind of the away piece. So is the source away? Is the observer moving away? That's the bottom part of the plus minus. All right. Are they moving towards, the source or whatever, or towards the observer? That's the top piece. Okay. So again, something to keep track of as you're kind of going through these. So now, how do we actually perceive sound? Well, again, it's that pressure change. So that pressure change is energy. It's energy over time. Energy over time is power. And there's only a certain amount of area that your ear can detect it. So there's a certain amount of intensity there. Power over area we call intensity. All right. It's also why different size speakers can have different size intensities. So now, as I look at those intensities, those powers over areas, the threshold of human hearing is very small, 10 to the negative 12 watts per meter squared. General conversations, about 10 to the negative 6th. We can get way up to loudest things that can hurt your eardrums, 10 to the 4th. Anything louder than that, wow, we could actually die from it. So I can go through this whole thing and understand now that the further I am away from the source, because the area actually goes out spherical, not flat, we basically start to, not double as I go further away, but I start to reduce my intensity by a quarter. And then, or if I triple it, I go down by a 9th. If I quadruple it, I go down by a 16th. So it's a over squared relationship. So remember we did that whole intensity thing with gravity. It's the same inverse squared relationship that the sound dissipates at. So our hearing is really versatile. So we can hear down to those whispers, those 10 to the negative 11th watts per meter squared. That gets into the fact of just like a displacement of only 10 to the negative 10th meters roughly the diameter of an atom that our hearing can detect. And that's when we're young, I might add, because as you get older, you start to lose some hearing. So our sound ratings are based on Alexander Graham Bell. He came up with a decibel. So the faintest sound a human can hear is 0 decibels. So if we double the intensity, that's a change of 3 decibels. If we double the loudness, that's a change by a factor of 10 decibels. Mathematically, this is a log-based relationship. And we use decibels again because the bell was too loud. So it's a ratio of 10 times the log of the intensity you're observing over the threshold intensity.